Hi, this is Mark Weitzman. I want to continue with a problem which uses the result that we just had. I'll write it down again when we need it. But let's just look at problem 1210A. First thing it asks for is G in units of light year per year. Those are strange units, but for these spaceship problems and stars, they tend to use those units. And then the second part of the problem is the spaceship accelerates at 1G. That means in its proper reference frame, it experiences like the same gravity that you would experience here on the Earth. So it feels 1G acceleration in its proper reference frame for 5 years. And then the question is how far and how fast is it going in the, and when we say 5 years here, this is all in the rest frame, not the spaceship frame, the rest frame. Let's call it the lab frame. Okay, so let me first do the easy part. The idea here is you should remember that G happens to be in units of 1 light year per year. Remember, light year is a distance of unit, is a unit of distance, and this is a unit of time, so that is a velocity. I'm sorry. This is G in units which use distance and time, but it's going to be light year per year squared. So let's evaluate G. G is equal to 9.81 meters per second squared. And 1 light year, I'll abbreviate it by LY, is equal to 9.46 times 10 to the 15th meters. Just take the velocity. If you don't know this number, take the velocity of light, multiply it by the number of seconds in a year, which is 1 year is equal to 3.16 times 10 to the 7th seconds. A lot of physicists remember this as just being pi. They write 3.15, pi times 10 to the 7th seconds, but 3.16 is a little more accurate. So substituting these numbers in here, you'll get G is equal to 9.81 meters times 1 light year divided by 9.46 times 10 to the 15th meters, and divided by seconds squared times 1 year over 3.16 times 10 to the 7th seconds. And this works out to 1.0355 light year per year squared. So that's the answer for that. And many times in these problems they just say assume it's 1, but we'll use the more accurate number. So for this problem we have a proper acceleration in the co-moving reference frame. We're going to have an acceleration of 1G. That means that the force in that reference frame that the rocket feels, the force, is going to be equal to mg. Just the usual Newtonian thing. There's no adjustment or anything because in the co-moving reference frame, the spaceship is always at rest, so there's no velocity. And this is a very important problem, this uniform force acceleration. It's used, sometimes it's called Rindler space-time. Rindler space-time, or Rindler acceleration. And it sort of describes the space-time around the black hole, right outside the horizon of a black hole. A Schwarzschild black hole. So that's sort of where it gets its importance. And because the force is constant, and we just showed in the previous problem, we showed that the force will be the same in the lab frame or in the rocket frame. So the force, let's call this in the rocket, the force in the lab is equal to the force in the rocket. That's equal to mg. And the problem we did last time was we showed that we know the solution for a constant force of mc squared over b. We know what the solution is. We know that x of t is equal to the square root of b squared plus c squared t squared minus b. And we could also differentiate that. We get that the velocity is the derivative of this c squared t over the square root of b squared plus c squared t squared. Yeah, see if I did that right. 1/2, I'm going to get c squared 2t, okay, yeah. So all we have to do is make the substitution mc squared over b equals mg. The m's cancel out, and so we get g is equal to c squared over b. And more importantly, b is equal to c squared over g. So if in these formulas we substitute b as c squared over g, we'll get the formula. Then substitute c equal 1, because the velocity of light is 1 light year per year, so c is 1, and t is 5. And when we do that, we get x of 5 is equal to 4.13 light years, and v of 5 is equal to 0.9819 light years per year, but that's the same as the velocity of light, c. So this is our answer for this problem. And in a sense, we're just using our solution from the previous problem. But what I want to do now is two things. I want to first show you in the next video, I'm going to show you how to prove that the forces are the same, even though we sort of verified it for one. Well, we didn't really verify it, we were told it. I want to explain why the force in the rocket flame and the force in the lab frame are the same. And then I want to show you an easier way to derive hyperbolic motion. So I'll see you next video.